Somewhere beneath the dark Atlantic, a sonar beam sweeps across what should be ordinary seafloor, and then the return signal simply disappears. Where solid limestone should echo back a clean reflection, there is nothing, a void, a gap in the profile that the instrument cannot fill because whatever is down there swallows the signal whole. The technicians mark it as a point of interest and move on to the next pass, but nobody goes in. Nobody even knows if going in is possible. That moment, a sonar return that drops away into silence, is how we first learn these places exist. And what lies on the other side of that silence, nobody can tell you. Not the divers who have worked these waters for decades, not the marine geologists who ran the surveys, not the biologists who suspect that something is living in there. The honest answer, repeated across every research paper and expedition log connected to these sites, is that the interiors are unknown. Scientifically, formally, operationally unknown. This is not a story about caves that explorers are working their way through. It is a story about sealed systems, structures identified from the surface, mapped by instruments that can measure their outline but cannot see inside them, sitting untouched beneath hundreds of meters of Atlantic water while the science community debates whether the technology even exists to reach them. Pull back to the scale of the problem, and the picture becomes genuinely strange. In 2009, NOAA launched an expedition specifically called the Search for Deep Water Caves, deploying high-resolution multi-beam sonar along Bermuda's shelf edge. The instrument flagged more than 100 points of interest, locations where consistent gaps in the acoustic profile suggested possible voids or overhangs beneath the seafloor. More than 150 limestone caves are known to exist in and around Bermuda. Of those, only a handful have ever been entered. The vast majority remain unmapped in their interiors, never open to divers, never penetrated by remotely operated vehicles. The sonar found the doors. No one has opened them. Move southwest to the Bahamas, and the scale of what might be hidden becomes harder to absorb. Seismic and bathymetric surveys of the Black Bahamian Escarpment revealed 29 giant abyssal depressions, elliptical features carved into the seafloor, ranging from 30 to 185 meters deep and stretching anywhere from 255 meters to nearly 2 kilometers across. Researchers interpret these as sealed submarine cave systems. Not one of them has been accessed by an ROV, not one has been entered by a diver. They sit at abyssal depths, their interiors scientifically untouched, known only by the shape their absence makes in the data. Closer to the American mainland, off Florida's continental shelf, there is a feature called the Red Snapper Sink, a vertical karst shaft that drops more than 400 feet into the seafloor before opening into a sand-filled basin at roughly 495 feet of depth. 2 technical dives in 1991 reached the bottom floor of the main shaft, and that contact is sometimes cited as evidence the site has been explored. But the lower chambers were only partially examined, and most of the interior remains unpenetrated. Whether you call that opened or not depends on your definition, and the definition matters, because the distinction between a brief bottom contact dive and a true scientific penetration of a cave system is enormous. What the 1991 divers found at the edge of what the sink contains is not the same as knowing what the sink contains. Here is where the pattern becomes visible. Bermuda, the Bahamas, Florida, 3 separate locations along the Atlantic realm, each one yielding features that share the same essential characteristics: deep, isolated, karstic in origin or interpretation, identified primarily through sonar or seismic gaps rather than direct observation, entrances either collapsed, too narrow for available equipment, or located at depths that place them beyond the practical reach of current technology, and interiors that remain, in every meaningful scientific sense, unknown. What researchers have is the shape of an absence, They know something is there because of the negative space it occupies in their data. They can estimate size, depth, rough geometry. They can look at the geological context and reason about how these structures likely formed. Some of them have found evidence of unique biological communities in the shallower, partly accessible cave systems nearby, organisms found nowhere else on the surface of the planet, and they have strong theoretical reasons to suspect that these sealed, deeper systems may harbour communities even more isolated and more unusual. But suspicion, however well-reasoned, is not observation. An observation requires getting inside. That is the investigation this requires, not just cataloguing what the sonar found, but working through what these structures actually are, whether the signatures represent true voids, collapsed depressions, or something harder to categorize, understanding why they have remained closed, whether by physics, by technology, by funding, or by legal frameworks that protect their surface without ever addressing their interiors, and confronting the possibility, held seriously by the researchers closest to this work, that what is sealed inside these systems may include life, geology, and chemistry that science has never had the chance to see. The sonar passes over the void, the signal drops away, the technician marks the location and moves on. Everything that follows is an attempt to understand what that gap in the data actually means, and what it would take to finally answer the question the seafloor is asking. Before anything else can be understood about these Atlantic features, the ones sonar found off Bermuda, the ones seismic surveys sketch beneath the Bahamas, the collapsed shaft off Florida, there is a more fundamental problem to work through. What exactly are we talking about when we say sealed underwater cave? Because depending on who is using that phrase and in what context, it can mean 4 or 5 entirely different things. And the differences are not minor. They determine whether a feature is scientifically significant, biologically relevant, practically reachable, and even legally protected. Collapsing all of them into one convenient label does serious damage to the actual picture. Start with the basic geological categories, because scientists who work in this region maintain strict distinctions that popular coverage almost never preserves. The first category is what researchers formally call a sea cave, and the terminology is immediately confusing, because a sea cave in the geologic sense is not necessarily carved by wave action at a coastline. In the Atlantic karst context, a sea cave refers to a passage that originally formed on dry land, likely during lower sea levels in glacial periods, and was subsequently flooded as the ocean rose. These passages often still contain speleothems, stalactites, stalagmites, the mineralized formations that only grow in air. Their presence is actually diagnostic evidence that the cave was once dry. When you find stalactites hanging in a flooded passage beneath the Atlantic, you're looking at a record of a different world. Bermuda's submerged cave systems contain exactly this kind of feature, and their geological character is fundamentally different from a simple depression in the seafloor. The second category is the karst sinkhole or blue hole, and this is where terminology starts generating real problems. A sinkhole is a vertical collapse feature, a pit that forms when underlying limestone dissolves and the ceiling drops. It may have no lateral passages at all. It might be a shaft straight down with a rubble floor at the bottom and nothing more. The famous Bahamian blue holes are often described interchangeably in popular media as caves, but the scientific literature is explicit that the two terms should not be used synonymously. A blue hole is a descriptor of colour and surface appearance. Whether it connects to a navigable cave interior is a completely separate question that requires actual penetration to answer. One research foundation studying Bahamian karst argued precisely this point in published work, noting that blue hole has become an inappropriate moniker that obscures the need for careful classification based on how the feature actually formed and what its internal geometry looks like. The third category is the flooded limestone conduit. what geologists call a phreatic passage, a tunnel that formed underwater along fracture lines in the limestone, guided by the chemistry of slightly acidic groundwater, dissolving the rock over geological timescales. These can extend laterally for kilometres. They are the features that cave divers most prize, because they have actual throughways, actual navigable geometry, actual space for a diver or a remotely operated vehicle to move through. Some of Florida's inland cave systems are the most famous examples in the world, but the same formation processes operated along what is now the submerged continental shelf when sea level was far lower and those limestone beds were exposed to freshwater infiltration. The fourth category is the abyssal pockmark, and this is where certainty starts to erode significantly. Pockmarks are elliptical depressions in the seafloor identified by sonar and seismic profiling. They can be caused by gas or fluid escaping from below, by sediment collapse, or by the dissolution of underlying material. The 29 features documented along the Black Bahamian Escarpment fall into this category in their initial description. They are enormous, up to 1.8 kilometers wide and 185 meters deep, and the seismic data reveals high amplitude anomalies beneath them that suggest collapse structures. Researchers interpret this as evidence of sealed submarine cave systems, but and this cannot be overstated, that interpretation is derived from remote sensing. No ROV has entered these features, no diver has approached them. The interior geometry is completely unknown from direct observation. Whether they contain navigable passages, whether they are simply collapsed depressions with no void space remaining, whether the sonar and seismic signatures reflect a true cave interior or a more complex geological structure, none of that has been confirmed by eyes or instruments that have actually been inside. This is the core uncertainty that every honest account of these features has to carry. Sonar can identify a void signature. Seismic reflection can suggest a collapse structure. But neither instrument can confirm that what lies beneath is a traversable cave rather than a rubble-filled basin, or a feature whose internal architecture is simply too irregular to call a cave in any meaningful sense. Now add to those four categories the question of what sealed actually means, because that word is doing a lot of work and it covers very different situations. In some cases, sealed means a physically collapsed entrance. Green Bay Cave in Bermuda has collapsed chambers, sections where the ceiling has dropped and blocked passage. The cave exists, it has been partially entered, but portions of it are closed off by fallen rock that would require either excavation or an alternative route to pass. That is one meaning of sealed. In other cases, sealed means sediment infill. Government Quarry Cave, also in Bermuda, has passages that end in sand, not rockfall but accumulated sediment that has gradually filled the conduit. The space beyond the sand may be open or it may be fully compacted. Without removing the sediment, nobody knows. In still other cases, sealed means depth. Red Snapper Sink drops more than 400 feet in a vertical karst shaft, and 2 technical divers reached the sand floor of the main chamber in 1991. That dive is sometimes described as the site being explored, which is technically accurate in the narrower sense but profoundly misleading in the broader one, because seismic profiles indicate a deeper breccia pipe extending to approximately 2,000 feet below the seafloor. That deeper structure has never been entered. Whether 1991's brief bottom contact penetration of the upper shaft constitutes opening the cave depends entirely on what you consider the cave to be. If the cave is the upper shaft, it was touched. If the cave includes everything beneath, it remains closed. This is not a trivial distinction, and differing interpretations of that ambiguity have led to genuinely contradictory claims in the literature about whether the site has ever been truly explored. And then there is the fourth meaning of sealed. No known human penetration of any kind, not because of physical obstruction, but simply because the feature is only a sonar-identified shape in the data, sitting at depths and distances that no expedition has yet addressed. That is the status of the 29 Bahamian pockmarks. They are not sealed by collapsed rock or sediment. They are sealed by depth, by remoteness, by the absence of any mission that has targeted them directly. This creates what can fairly be called a grey zone across the Atlantic shelf, a collection of features that exist somewhere between confirmed cave and mere depression, between scientifically verified void and unverified sonar signature. Bermuda's deep water limestone caves are mapped by sonar but lack reachable entrances. The Bahamian pockmarks have shapes consistent with collapsed karst, but no confirmed interior passages. Red Snapper Sink has a documented upper chamber and a hypothetical lower structure that exists only in the seismic record. The problem is compounded by how these features are discussed outside scientific literature. Media accounts reach for the most dramatic available language, sealed caves, hidden caverns, underwater mysteries. And those descriptions are not wrong, exactly, but they carry an implication of certainty that the data does not support. A sonar anomaly that suggests a void is not the same as a cave. A pockmark that resembles a collapsed structure is not the same as a proven conduit. A depth barrier that prevents entry is not the same as a solid wall. What this means practically is that before asking what is inside these features, science has to establish more rigorously what kind of feature each one actually is. The categories matter, the distinctions matter, and the honest answer, repeated across nearly every relevant research paper, is that for many of these sites, the classification itself remains unresolved, because resolving it requires the kind of direct access that the seals, whatever form they take, have so far made impossible. So where do all of these features actually come from? What process produces a sealed underwater cave system sitting on the Atlantic shelf, or a collapsed karst shaft dropping hundreds of feet into the Florida seafloor, or a field of giant depressions along the Bahamian Escarpment? The answer requires going back in time, much further back than most people expect, and understanding that the Atlantic coastline we see today is not the Atlantic coastline that existed for most of the last several 100,000 years. The key is ice. During the Pleistocene epoch, which stretched roughly from 2.6 million years ago to about 11,700 years ago, the Earth cycled repeatedly through glacial periods. During the coldest phases, enormous volumes of water were locked in continental ice sheets, and as a result global sea levels dropped dramatically. At the peak of the last glacial maximum, around 20,000 years ago, sea levels stood somewhere between 100 and 130 meters lower than they do today. To put that in physical terms, the continental shelf, the shallow, gently sloping platform that now lies submerged off the eastern coast of North America, was dry land. The shoreline of what is now the southeastern United States extended miles further east into what is now the Atlantic Ocean. Bermuda's limestone platform, now largely submerged, sat exposed to open air. The carbonate banks of the Bahamas rose above sea level as islands. These were not minor changes. They were fundamental reorganizations of the landscape, and they lasted long enough, tens of thousands of years in some cycles, to profoundly reshape the geology of whatever rock happened to be sitting there. That rock, across all three of these regions, is limestone. And limestone, uniquely among common rock types, is soluble. Not quickly, not dramatically, but persistently and comprehensively over geological timescales. Rainwater, as it falls through the atmosphere, absorbs carbon dioxide and becomes a dilute carbonic acid. When that slightly acidic water percolates down through limestone, it dissolves the calcium carbonate, slowly widening fractures, enlarging joints, carving out horizontal voids and vertical shafts. This process, called karstification, is the engine that produces cave systems. It requires time. it requires limestone, and it requires exposure to fresh water. During those Pleistocene low stands, all three of those conditions were satisfied along what is now the Atlantic shelf, and across all three of the regions under discussion here. Bermuda's situation is particularly well documented. The island is built on an ancient volcanic seamount that has been capped with eolianite, limestone formed from wind-blown carbonate sand, compressed and cemented over time. This limestone cap, somewhere between 15 and 100 meters thick depending on location, was fully exposed during glacial low stands. Rainwater worked through it continuously, dissolving lateral voids, creating underground drainage networks, depositing speleothems, stalactites and stalagmites, in air-filled chambers. The stalactites are the giveaway. They can only form in air. Their presence in passages that are now completely submerged is direct evidence that those passages were once dry, that they formed on land, and that the ocean came to them later. When post-glacial sea levels rose, water flooded these cave systems, halting dissolution and preserving whatever geometry had developed up to that point. Roof collapse in some areas produced breakdown chambers, and in others that collapse created the physical seals that now block entry. The Bahamian carbonate platform has a more complex story, though the fundamental driver is the same. During low stands, meteoric groundwater, meaning fresh rainwater that had percolated into the platform, entered the carbonate system and began dissolving it from within. But the Bahamian geology adds another layer of complexity. Along fault-controlled conduits through the platform, a process of brine convection appears to have allowed corrosive salt water to work on the carbonates from below, while fresh water worked from above. The combination was particularly aggressive at dissolving carbonates and evaporites, creating large collapse structures. These are what the 2020 preprint examining the Black Bahamian Escarpment identified as those 29 giant pockmarks, features ranging from 30 to 185 meters deep and up to 1.8 kilometers wide. The researchers interpreted the high-amplitude seismic anomalies beneath the pockmarks as evidence of collapse structures, and the dimensions and geometry as consistent with sealed submarine cave systems produced by exactly this kind of dissolution and subsequent marine transgression. That interpretation remains contested, and whether these features represent true traversable voids or simply collapsed depressions is precisely what direct exploration would need to determine. But their origin story, dissolution during low stands, flooding, collapse, sealing, fits the same karst template operating in Bermuda. Florida's red snapper sink adds a third geological dimension. This offshore shaft cuts through multiple distinct rock formations in sequence. Quaternary sands on top, then the Miocene Hawthorne Formation, then the Eocene Ocala limestone beneath that, with seismic data suggesting the pipe's origin lies somewhere around 2,000 feet down in Upper Cretaceous and Paleocene rocks. That depth is significant because it means this structure is not simply a surface dissolution feature. It is a karst breccia pipe, a collapse that propagated upward through multiple rock layers as underlying material dissolved and the overlying column lost its support. The Ocala limestone is a thick, regionally extensive carbonate formation that underlies much of Florida's submerged shelf, and it was aggressively karstified during the same Pleistocene low stands that shaped Bermuda and the Bahamas. The upper shaft that divers reached in 1991, the 400-foot vertical drop with the undercut limestone roof, and the small caverns observed at the base where water was seen flowing inward, is just the visible top of a structure that the rock record suggests extends far deeper and remained active across multiple geological periods. What connects all three sites, despite their different surface expressions and their different geological specifics, is this shared sequence of events. Thick carbonate platforms accumulated over millions of years, Sea levels dropped during glacial cycles. Fresh water infiltrated the exposed rock and began dissolving it. Voids grew, laterally in some places, vertically in others, along fault lines and fracture networks and bedding planes where the chemistry was right and the pathways existed. Then sea levels rose again and the voids were flooded. Sediment accumulated, some roofs collapsed, some entrances became blocked by fallen material, others simply descended below depths that any human technology of the time could reach. This is why these features survive as inaccessible relics. Sealed under deep water, often in anoxic conditions where biological decay operates slowly or not at all, some of these systems have been preserved in essentially their flooded state for thousands of years. The structures that formed during the Pleistocene low stands were locked in place by the marine transgression, protected from the erosional forces that would have modified them if they had remained exposed on land. The very process that ended their formation also archived them. The ocean, by flooding these systems, turned them into time capsules of a different Earth. The challenge is that geological preservation and human accessibility are two entirely different things. A cave system that has survived 10,000 years of submersion in the Atlantic may be extraordinarily intact, but if it sits at 300 meters of depth with a collapsed entrance and anoxic water inside, the fact of its preservation offers nothing to the researchers who want to study it. The processes that formed these systems are well understood. The general geometry is beginning to emerge from sonar and seismic data, but the interior, what is actually inside, what the geometry looks like at human scale, what chemistry the water carries, what might be living in the dark, remains on the far side of a seal that the forming process itself helped create. Bermuda sits at the center of some of the most concentrated and best documented submarine cave research ever conducted in the Atlantic. It is also, in a fundamental way, a perfect illustration of the gap between knowing something exists and actually being able to reach it. Starting in 2009, NOAA launched a program specifically designed to find out what was hiding beneath Bermuda's submerged limestone platform. The program, formerly titled The Search for Deepwater Caves, ran through 2011 and represented one of the most systematic attempts to inventory submerged karst features in the Atlantic realm. Researchers combined high-resolution multi-beam sonar surveys with remotely operated vehicle inspections and, where possible, direct diver entry. When the mapping was complete, the numbers were striking. More than 150 limestone cave features had been identified around Bermuda's shallow platform. The 2011 phase of the expedition alone flagged 161 distinct points of interest: potential cave entrances, sinkholes, undercut ledges, scattered across the main platform and extending out to Challenger Bank, the submerged seamount that rises to within a few meters of the surface, about 20 kilometers southwest of the main island. That is a remarkable density of features for a relatively small oceanic island, and it reflects exactly the geological history laid out in the previous section. Eolinite limestone built up over the volcanic seamount, karstified during Pleistocene low stands when the platform sat exposed to rainwater and open air, then drowned by post-glacial sea level rise. The stalactites and speleothems found in some of Bermuda's known cave systems confirm that these passages were once air-filled. They are not marine formations, they are terrestrial features that the ocean claimed. But here is where the gap between mapping and access becomes real. Of those 150-plus identified cave features, only a handful have ever seen a human diver. Not partially explored, actually entered. The first confirmed deep-water diver entry during the entire program happened on June 13, 2011, when divers penetrated Green Bay Cave, a site on the main platform. The following day, June 14, a second dive explored what's recorded as Deep Blue Cave within the Walsingham Cave System, a limestone complex on Bermuda's eastern end. 2 dives, 2 sites. Out of more than 150 mapped features, those were the documented entries. That contrast, 150 mapped, 2 entered, is not a failure of the program. It is an honest reflection of the physical conditions that the program encountered when it tried to move from identification to access. The ROV surveys help explain why. During 6 days of ROV operations in 2011, researchers were able to inspect 25 of the highest priority points of interest identified by the sonar surveys. What they found at many of those sites were small tubular passages at depths typically ranging from around 107 to 128 meters. Some appeared to penetrate further into the rock. Some showed the kind of geometry you would expect from flooded dissolution voids: rounded profiles, sediment-filled floors, the architectural signatures of caves formed in air and then drowned. But the ROV could look into these openings. It could not follow them. The passages were too narrow, the geometry too complex, and the depth too great for the remotely operated vehicle technology available at the time to do more than confirm that something was there. For human divers, the situation is even more constrained. Cave diving at depth is one of the most technically demanding forms of exploration that exists. It combines the physiological challenges of deep diving, gas management, decompression obligations, nitrogen narcosis, oxygen toxicity, with the navigational and physical challenges of penetrating an enclosed space with no direct access to the surface. Even with the most advanced mixed gas rebreather systems available, the combination of depth, passage geometry, and limited bottom time at Bermuda's deeper cave sites pushes most of those passages beyond what is safely reachable. The effective ceiling for current cave diving technology in these conditions sits somewhere around 200 meters at the extreme edge of capability, and many of the Bermuda features extend well beyond that range. Add collapsed entrances, passages where roof breakdown has blocked or narrowed the entry point, and the barriers compound. A passage that sonar shows as a void behind a collapsed threshold might as well not exist from a diver's practical standpoint. It is worth being precise about what the sonar data actually tells us and what it doesn't. Multi-beam sonar identifies variations in seafloor geometry, changes in depth, slope, and return signal intensity that can indicate the presence of voids, undercuts, or openings in the rock. What it cannot do is confirm that those features are traversable caves rather than shallow depressions, pockmarks, or partial collapses with no significant interior void. Some of the 150-plus features mapped around Bermuda may ultimately prove to be minor ledges or sediment-filled depressions rather than true cave systems. The program's researchers were careful about this, classifying many sites as points of interest rather than confirmed caves. That epistemic honesty matters. The real number of genuinely open, traversable sealed cave systems in the Bermuda platform is almost certainly smaller than 150. It may also be much larger than the 2 sites that have been entered. The honest answer is that we don't know, and we don't know precisely because we cannot get inside. What makes Bermuda particularly significant as a case study isn't just the number of features identified, it's the combination of documented existence, partial investigation, and unambiguous inaccessibility that makes it the strongest real-world example of the broader phenomenon under discussion in this video. These are not speculative features inferred from geology alone. They are features that sonar has mapped, that ROVs have photographed at their entrances, that in 2 cases human divers have actually entered, and yet the vast majority of them remain, in any meaningful sense, unopened. The interiors are unknown, the extent of the passages is unknown, the chemistry of the water inside the sealed sections is unknown. Whether those deeper, unmapped passages connect to one another, Whether Bermuda's submerged limestone conceals something approaching a coherent underground network is unknown. What the biological surveys of the caves that have been entered suggest is that the stakes of that unknowing are not trivial. The known Bermuda caves, including sections of the Walsingham system, host specialized stygobiont communities. Organisms adapted specifically to subterranean aquatic environments, many of them found nowhere else on Earth. These enchyoline fauna, crustaceans, isopods, and other invertebrates that have evolved in isolation over geological timescales, represent a kind of living record of biological adaptation under extreme conditions. If the accessible caves contain these communities, the reasonable inference is that the deeper, sealed passages contain related fauna that have had even longer periods of isolation and may have diverged even further from their surface relatives. That is a hypothesis. It cannot be confirmed until someone gets inside, but it is a hypothesis grounded in the consistent pattern of what cave biology has found everywhere it has been able to look in similar systems. So Bermuda is where the abstract concept of a sealed underwater cave becomes concrete. The NOAA expeditions gave us numbers and locations. The ROV surveys gave us images of thresholds. The 2 diver entries in June 2011 gave us a brief glimpse past those thresholds into what the sealed systems look like from the inside, and then the depth and the collapse and the technical limits of current technology drew a line, and everything beyond that line remains on the far side of a seal that has been in place since the Atlantic Ocean reclaimed this platform at the end of the last ice age. More than 150 features mapped, 2 entered, the rest waiting. So let's go inside the 2 systems that have actually been entered and look carefully at what explorers found and where they were stopped. Green Bay Cave is the clearest example of what successful entry into Bermuda's submarine karst actually looks like. The system has 2 sea-level entrances, and divers have surveyed more than 2 kilometers of passage, making it the most thoroughly documented deep-water cave in Bermuda's network. The passages run at depths of roughly 18 to 20 meters, shallow enough that conventional cave diving equipment and mixed gas configurations can manage both the bottom time and the decompression obligations. Inside, the biological zonation is visible. Communities shift as you move from the entrance zone, where surface light still penetrates, into the interior, where conditions become increasingly isolated from the outside ocean. It is, by any standard, a significant cave system. It is also, in the context of Bermuda's broader network, something closer to an outlier than a representative sample, accessible precisely because its geometry and depth happen to fall within the range where current technology can operate. The Walsingham system tells a more complicated story. It extends approximately 1.3 kilometers and is served by 7 entrances, though only 2 of those entrances are accessible to tourist divers, and full penetration of the system requires considerably more technical preparation. The Walsingham links to the adjacent Palm system through what appears to be a collapse origin saddle, a section of passage where the original cave ceiling is fractured and partially fallen, creating a connection between 2 networks that were likely formed independently and then joined by breakdown. The Palm system has 5 entrances of its own, and strong tidal currents run through it, complicating penetration. Guidelines laid in earlier dives have degraded, and visibility in the tidal sections is frequently poor. So even within the systems that qualify as entered, there are significant portions that remain effectively closed, passages that have been identified by ROV and sonar survey as continuing beyond accessible chambers, but that narrow to passages of 1 meter or less in width, or that disappear behind collapse zones where the roof material has fallen and blocked the way forward. Explorers know those passages continue. They cannot follow them. This is the critical distinction that gets blurred in any broad summary of Bermuda's caves. The difference between a cave being entered and a cave being fully explored. Green Bay has been surveyed for 2 kilometers of passage. That is not the same as saying that 2 kilometers is the full extent of the system. The passages known to continue beyond surveyed endpoints, narrowing or deepening or disappearing into breakdown, represent a category of their own, identified but not entered, documented at the threshold but unknown beyond it. And the Walsingham system's known offshoots, identified during ROV survey operations, fall squarely into this category. Sonar and remotely operated vehicles can image the entrance to a passage. They cannot tell you where it goes. The 2011 dive on Challenger Bank makes the depth problem viscerally concrete. In June of that year, a mixed gas closed-circuit rebreather team conducted what became the deepest manned dive of the entire program, reaching 444 feet, approximately 135 meters, on the Challenger seamount. At that depth, with the full weight of technical support required to get a diver there and back safely, the team located what appeared to be a potential cave opening in the seamount rock. What they found inside was a series of small alcoves, no significant chamber, no traversable passage extending further into the rock. The effort required to reach 135 meters at that site was substantial, and the return was, geologically speaking, modest, which is precisely the point. The Challenger seamount is not a failure of exploration planning or diver capability. It is an accurate demonstration of where the current technical frontier actually sits. At depths above roughly 100 meters, cave diving in this environment shifts from difficult to extraordinarily demanding. Helium-rich gas mixes are required to manage narcosis and oxygen toxicity. Rebreather systems must be configured and maintained for deep water operation. Decompression obligations on the ascent become extensive, extending the total dive time well beyond what bottom time alone would suggest. And all of this is before accounting for the actual cave environment, the confined geometry, the potential for silt disturbance to eliminate visibility entirely, the physical effort of moving through tight passages in full technical dive equipment. The practical ceiling for human cave diving under these conditions sits somewhere in the vicinity of 200 meters as an extreme outer boundary of what is currently possible, and reaching that ceiling requires everything to go right. Many of the Bermuda features that sonar has identified lie deeper than that, or present passage geometries that make human entry impossible regardless of depth. For ROVs, the barriers are different, but equally real. The vehicles available during the NOAA expeditions were capable of inspecting cave entrances at the depths encountered. The ROV surveys documented 25 high-priority sites during 6 days of operations in 2011. But inspection is not penetration, a passage entrance that measures less than a meter across, or that bends sharply shortly after the opening, or that is partially blocked by a collapse pile, presents an effective barrier to an ROV just as it does to a diver. The ROV can look in, it cannot go further, and the images it captures at those entrances, tubular passages, rounded profiles, sediment-covered floors visible for a few meters before the passage curves away into darkness, confirm that something is there without revealing anything about what that something contains. This brings us to the honest accounting of what exploration has actually established, versus what remains inference from remote data. The sites where direct observation has occurred are Green Bay Cave, Natural Bridge, sections of the Walsingham and Palm systems accessible to technical divers, and the Challenger Bank seamount dive. These sites have been entered, in varying degrees, by human divers. What has been directly observed is a function of where those divers were able to go, which is a function of depth, passage width, collapse geometry, and available technology. Everything beyond those accessible sections, the offshoots identified by sonar and ROV, the deeper passages behind collapse thresholds, the cave features on the outer platform that have never had a diver near them, is known only through remote imaging. And as the NOAA researchers were careful to note, Remote imaging from multi-beam sonar cannot definitively distinguish a traversable cave passage from a pockmark, a shallow surface depression, or a collapse zone with no significant interior void. The 150-plus features mapped around Bermuda include sites ranging from confirmed cave passages to features whose status as true caves remains genuinely uncertain. What the successful entries did in practice was deepen the mystery rather than resolve it. Green Bay's 2 kilometers of surveyed passage end at points where the system continues beyond reach. Walsingham's mapped offshoots remain unpenetrated. The Challenger Bank dive confirmed that cave-forming conditions exist at depth on the seamount and found nothing significant, which means the question of what deeper features on that structure actually contain is no more answered than it was before the dive. Each entry produced real data and real understanding of what Bermuda's submarine karst looks like from the inside. Each entry also clarified exactly where the limits of current access fall, and what lies on the other side of those limits. A pattern emerges from all of this that is more informative than any single data point. Bermuda's explored caves are windows, genuine, scientifically valuable, biologically rich windows, into a system that extends well beyond what any window can show. The passages that continue past the surveyed endpoints of Green Bay, the offshoots behind Walsingham's collapse zones, the dozens of remotely imaged features that have never had a diver within kilometers of their entrances. These are not gaps in the exploration record that better planning would have filled. They are the product of hard physical limits, and they mark the boundary between what has been reached and what, for now, remains sealed. Bermuda's limits, then, are not unique to Bermuda. They represent a broader problem along the Atlantic realm, the gap between what remote sensing can detect and what any existing technology can actually reach and enter. And if you move south and west from Bermuda, following the edge of the carbonate platform system that underlies much of the western Atlantic, you arrive at a place where that problem becomes dramatically larger in scale. The Bahamas sit atop one of the thickest sequences of carbonate rock on the planet. Thousands of meters of limestone laid down across hundreds of millions of years of shallow tropical sea form the foundation of the Bahamian platform. The edges of that platform drop off steeply into the deep Atlantic, and it is along one of those steep edges, a feature called the Bahamian Escarpment, that researchers working with multi-beam sonar and high-resolution seismic data made a discovery that has not received anything like the public attention it deserves. 29 depressions. That is what the acoustic surveys found, spread along the base of the escarpment where the Bahamian carbonate platform meets the abyssal Atlantic floor. 29 distinct features, each one a deep enclosed depression in the seafloor, mapped using data from the Carambar research cruises. On the surface, the count alone is striking. But the dimensions are what make these features genuinely extraordinary. The depressions range from roughly 30 to 185 meters deep, measured from their rims to their floors. In width, they span from approximately 255 meters at the smaller end to nearly 1.8 kilometers across at the largest. Set those numbers against anything familiar, and the scale becomes concrete. The largest of these features, at close to 2 kilometers wide, would comfortably contain the footprint of a small city neighborhood. And they sit in water that is itself already between approximately 4,580 and 4,970 meters deep, well into the abyssal zone, at depths where ambient pressure alone makes any kind of physical access an extraordinary undertaking. The morphology of these features, as revealed by the acoustic data, is not random. The depressions are elliptical in shape and are aligned with structural lineaments, faults and fracture zones, running through the Bahamian Escarpment. That alignment is significant because it connects the geometry of the features to the underlying geology of the carbonate platform rather than to surface processes or random sediment dynamics. Researchers interpreting this data have proposed that these depressions are best understood as sealed karstic sinkholes, dissolution cavities formed by hypergenic processes, meaning the dissolving fluid moved upward through the rock from below rather than downward from the surface. This is the same family of processes that produces some of the largest cave systems on land, where deep circulating fluids eat away at carbonate rock from the interior outward, sometimes producing chambers of extraordinary size before the surface ever shows any sign of what is developing beneath it. The interpretation that follows from this analysis is that at least some of these features may represent genuine sealed submarine cave systems, enclosed underground voids of enormous volume, capped by rock that has not yet failed, sitting in the deep ocean where no light reaches and where no human technology has yet arrived. That is the hypothesis, and it is important to be precise about what the word hypothesis means here, because the evidence for it is entirely acoustic. Every piece of data gathered on these 29 features has come from remote sensing, multi-beam sonar, chirp profiling, seismic reflection surveys. These tools can map the exterior geometry of a depression with considerable precision. They can suggest something about the subsurface structure, whether solid rock lies beneath, or whether there is an indication of void space that the seismic wave passes through differently. But they cannot confirm the interior of a sealed feature. No remotely operated vehicle has descended into any of these depressions. No submersible has approached them. No diver has been anywhere near them. The interiors of all 29 features are, as of now, completely unvisited and completely unknown. This is not a minor caveat attached to an otherwise well-documented situation. It is the central fact. The distinction between a sonar-mapped depression and a confirmed cave is fundamental, and it has not yet been bridged at the Bahamian Escarpment. What the acoustic surveys detected could be exactly what the karstic sinkhole interpretation suggests: sealed underground voids of a scale rarely encountered anywhere on the planet. Or some portion of these features could be fluid escape pockmarks, structures created when pressurized gas or water blows through soft sediment and leaves a depression that resembles a sinkhole in acoustic profile without having any significant void beneath it. Or they could be collapsed structures, places where a cave ceiling once existed but has long since fallen, leaving a topographic depression without any remaining interior space. The honest scientific position is that the instruments used so far cannot definitively distinguish between these possibilities for features whose interiors have never been directly sampled. What makes the Bahamian features particularly significant, even within that uncertainty, is the scale at which they operate. If even a subset of these 29 depressions are genuine sealed cave systems, they would rank among the largest unvisited underwater voids recorded in the entire Atlantic realm. The largest known underwater caves explored by humans, the Sacacton system in Mexico, the caves of the Yucatan Peninsula, are measured in hundreds of kilometers of surveyed passage, but they have been entered, explored and mapped over decades of sustained effort. What sits at the base of the Bahamian Escarpment has never been entered at all, and the individual chamber volumes implied by depressions nearly 2 kilometers wide and 185 meters deep would place them in a category of their own. The depth at which they sit makes the access problem qualitatively different from what confronts cave divers in Bermuda or Florida. 5 kilometers of water column above a cave entrance is not a technical challenge that better mixed gas ratios or more capable rebreather systems can solve. It is a problem that requires deep-sea submersibles with the pressure tolerance and maneuverability to operate at abyssal depths, combined with the kind of cave penetration capability that currently does not exist in any single vehicle. The ROVs and submersibles that operate routinely at these depths are designed for open water observation and sampling, not for navigating confined cave passages of uncertain geometry, and the cave passages themselves, if that is what they are, sit beneath a sealed rock surface whose structural integrity is unknown, in an environment where the consequences of equipment failure are unrecoverable. So the Bahamas presents a version of the sealed cave problem that exceeds Bermuda's in almost every dimension. The features are larger, the depths are greater by an order of magnitude, the access requirements push well beyond current operational capability, and the question of whether what the sonar found is actually a cave rather than a pockmark or a collapse depression cannot be answered without physical entry, which requires technology and logistics that do not yet exist in deployable form. What the Karst surveys accomplished was to draw attention to the possibility. 29 features mapped along the escarpment, their dimensions measured, their alignment documented, their potential origin argued in peer-reviewed literature. The data sits there, precise and detailed in acoustic terms, and completely silent on the one question that matters most. What, if anything, occupies the sealed space beneath those rims? Whether the Bahamas conceals some of the largest unopened underwater voids in the Atlantic, or a series of geological depressions that look like caves from a distance but contain nothing, is a question that current knowledge cannot answer. And that uncertainty, extending across features of this scale, in a region this geologically significant, is one of the more remarkable gaps in what we actually know about the ocean floor beneath Atlantic waters. The uncertainty just described is not a temporary inconvenience waiting to be resolved by the next research cruise. It reflects something structural about how ocean science works, about the gap between what instruments can measure and what physical reality actually contains. And it is worth pausing on that gap because the Bahamian features are a particularly clear example of a problem that runs through the entire field of submarine karst research. Start with what the acoustic surveys can actually establish. Multi-beam bathymetry produces a high-resolution map of the seafloor surface. It works by sending out fans of sonar pulses and recording the return times and angles, building up a detailed picture of elevation and shape across wide swaths of the ocean bottom. For the 29 depressions along the Black Bahamian Escarpment, multi-beam data is genuinely informative. It tells you the dimensions of each feature, the width, the depth from rim to floor, the overall shape of the basin. It tells you that the features are elliptical rather than circular or irregular. It captures the steepness of the walls and the alignment of the depressions along structural lineaments in the underlying rock. That is not trivial information. The geometry revealed by multi-beam surveys is consistent with karst dissolution, with the kind of collapse and void development that produces enclosed sinkholes rather than simple erosional basins. The size of the largest features, close to 2 kilometers across and nearly 185 meters from rim to floor, puts them in a range that pockmarks from shallow gas escape do not typically occupy. Large, steep-walled, structurally aligned depressions in thick carbonate rock are the morphological signature of something more than surface sediment disturbance. But multi-beam stops at the surface. It images what is there, the exterior topography of the depression, and says nothing about what lies beneath the seafloor within or around it. For that, researchers rely on seismic profiling, which sends acoustic energy into the rock column and records how it reflects back from subsurface boundaries. Seismic reflection data can reveal layering in the rock, faults, and zones where the physical properties change, including zones where acoustic energy passes through differently, because void space or fluid-filled cavities are present. The Karst survey data includes seismic profiles across these features, and the results show high-amplitude anomalies beneath several of the depressions. That kind of anomaly is one of the signatures that can indicate a buried void or a gas-charged zone below the seafloor. It is suggestive. It raises the probability that something structurally significant is present at depth. What seismic profiling cannot do is close the argument. Seismic data is inherently indirect and inherently ambiguous when applied to questions of cavity geometry. The same anomaly that might indicate a roofed void could also reflect a dense carbonate bench, a change in sediment composition, or a fluid-saturated layer with no void space at all. Researchers working with submarine karst features have documented this problem explicitly. The multi-solution problem, where a single seismic signature is consistent with several different physical configurations, and the data alone cannot select between them. For the Bahamian depressions, the high-amplitude anomalies beneath the basins are consistent with the hypothesis that roofed void systems persist at depth, possibly beneath a carbonate bench that has not yet collapsed. But consistent with is not confirmed by, and that distinction is the entire problem. What makes the geometry compelling, and what keeps the sealed cave interpretation alive despite the lack of direct evidence, is the combination of factors taken together: steep walls, large enclosed basins, carbonate substrate known to support karst dissolution, alignment with structural faults that would have channeled dissolving fluids through the rock over geological time, seismic anomalies beneath the features. Each of these individually could have an alternative explanation. Together they produce a profile that matches the expected appearance of a karst sinkhole system with a degree of consistency that researchers have taken seriously enough to put into the scientific record. The authors of the Carambar analysis explicitly raise the possibility that the high-amplitude anomalies represent buried carbonate benches concealing roofed voids that later partially collapsed, meaning that the depressions visible at the surface might represent only the uppermost expression of a larger sealed system that extends downward into the rock. That interpretation remains plausible. It also remains unconfirmed. The three competing interpretations, fluid escape pockmarks, collapsed depressions with no remaining void, and roofed karst shaft systems still sealed at depth, all have some basis in the available data, and the available data cannot eliminate any of them. Fluid escape pockmarks are produced when overpressured gas or water escapes upward through soft sediment, forming bowl-shaped depressions at the surface. They're common on continental margins worldwide, but the scale of the Bahamian features, particularly the largest ones, exceeds what shallow pockmark formation typically produces, and the structural alignment is not a pattern usually associated with diffuse gas escape. Collapsed depressions where a cave ceiling has failed and the void has been largely filled by rubble and sediment would explain the surface morphology without requiring any intact interior space. This is a real possibility, and the fact that the features exist at all could be interpreted as evidence of past cave development rather than ongoing sealed chambers, but it does not preclude the possibility that collapse was partial, that some void remains beneath the rubble, and the seismic anomalies leave that door open. None of this will be resolved by more acoustic surveys. More refined multi-beam data will produce more precise surface geometry, but it will not tell you what is under the floor of a depression. Better seismic processing might sharpen the anomaly signatures, but it will not eliminate the multi-solution ambiguity that is inherent to indirect subsurface imaging. The only way to determine whether any of these features contains an intact sealed void is to go there physically and look. That requires an ROV or submersible capable of operating at nearly 5 kilometers depth with the navigation and sampling capability needed to approach, examine, and potentially enter a confined structure. It requires logistics of a scale that no expedition focused on these features has yet mounted, and it requires that the feature actually be enterable, that if a roofed void exists, there is some opening large enough to admit an instrument package. None of those conditions have been met, No ROV has visited any of the 29 depressions. No submersible has descended to the Bahamian Escarpment with the intent of physically investigating these features. The claim that they are unentered rests on the absence of any published penetration record, which is not quite the same as a guarantee that no brief bottom contact pass has ever occurred. But it is the best available evidence, and the scientific literature treats these features as unvisited. Their interiors are, in any meaningful sense, unknown. What the Bahamian pockmarks illustrate is something broader about how the deep Atlantic seafloor gets interpreted. Most of what we know about the geology of the deep ocean has been assembled from instruments that never touch the features they study. Acoustic mapping, seismic profiling, remote sensing from surface ships or towed arrays. These tools have produced an extraordinary picture of a world that very few people have physically visited, and that picture is detailed enough to generate confident-sounding interpretations. But interpretation is not observation. A feature identified on a sonar record as a probable karst sinkhole is still a hypothesis until someone descends into it and finds out. The 29 depressions along the Bahamian Escarpment are, right now, 29 hypotheses sitting on the deep ocean floor, large enough to be extraordinary if the sealed cave interpretation is correct, and entirely unresolved because no instrument yet used has been capable of settling the question. The Bahamian depressions sit at depths that place them beyond most operational dive technology, which is part of why they remain entirely unvisited. But you do not have to go to abyssal depths to find sealed submarine karst on the Atlantic coast. Roughly 42 kilometers east of Crescent Beach, Florida, in water that begins at a comparatively modest 88 feet, there is a feature called Red Snapper Sink. It sits on the continental shelf, well within the range that technical divers can reach. It was visited, dives were made, a floor was touched, and despite all of that, the interior of Red Snapper Sink remains, in any meaningful sense, unknown, which makes it one of the more instructive cases in Atlantic submarine cave research, precisely because it forces a more careful answer to the question of what it means for a cave to be opened. The surface expression of Red Snapper Sink is a circular depression, roughly 400 feet across, sitting in that 88-foot depth at the seafloor. That is the mouth. Drop below it, and the feature becomes a vertical shaft, narrower than the opening, somewhere in the range of 150 to 170 feet wide, that bores straight down through geological time. The walls cut through Miocene hawthorn sands, through younger sedimentary layers, and continue downward until they reach the top of the Ocala limestone at around 380 feet below the surface, where the geometry of the shaft changes and the walls become undercut, pulling back from a plumb vertical drop into something more complex. 400 feet, nearly 500 in its deepest measured section, a shaft carved by dissolution through the carbonate rock of the Florida platform, sitting on the open shelf as a direct window into the subsurface geology of one of the most extensively karstified regions in North America. The 1991 exploration work is where the story becomes particularly precise and particularly instructive. Technical divers made the first bottom contact dives into Red Snapper Sink that year, reaching a sand-covered floor at depths between 434 and 460 feet. A subsequent dive reached 482 feet and documented something significant: seawater seeping through small caverns at the base of the shaft. These small openings were observed, they were photographed, and they were not entered. The geometry was too tight, the depth too extreme, the physiological and logistical constraints of the dive too demanding to permit anything beyond visual and physical contact with the outer edge of those smaller chambers. What the 1991 divers saw at the bottom of Red Snapper Sink was the threshold of something, not the end of the feature, but the beginning of a deeper phase that no one has yet been able to follow. This is where red snapper sink sits in an uncomfortable middle category. It is not like the Bahamian depressions, which have never had any physical instrument contact whatsoever. Divers were there. They reached the floor. They observed the seeps and the small caverns. That counts as something. But it does not count as interior penetration, and the distinction matters. The caverns visible at the shaft base were not mapped. Their extent was not measured. Whether they connect to larger voids beyond the first few meters of the opening, whether there is a developed anculin system, a maze of solution passages, a deeper chamber, none of this is known. Contact with the threshold is not the same as knowledge of what lies beyond it, and the interior of red snapper sink, below the level where the shaft walls become undercut and the small openings appear, has never been entered. The geological context makes this gap in knowledge more significant, not less. Seismic profiles of the feature and the surrounding rock suggest that red snapper sink is not simply a shallow collapse pit that happens to be filled with seawater. The data points toward it being the surface expression of a karst breccia pipe, a structure created by repeated dissolution and collapse, extending deep into the underlying rock, potentially originating more than 2,000 feet down in Upper Cretaceous and Paleocene formations. What that means, if the seismic interpretation holds, is that the shaft visible at the surface is the uppermost section of a feature that may develop far beyond any depth that has been measured or observed. The sand-covered floor that the 1991 divers touched, the small caverns at its edges, the seeping water, these may represent the narrow upper expression of a much larger system, rooted deep in ancient carbonate rock. Seismic data is indirect, and the same caveats apply here that apply to the Bahamian features. What acoustic energy returning from depth can tell you, and what it cannot. The breccia pipe interpretation is consistent with the data. It is not confirmed by it. The actual geometry and extent of any deeper development cannot be established without physical access, and physical access to that zone does not exist. The caverns at the base of the shaft are sealed in a practical sense, not by a single impenetrable barrier, but by the accumulated constraints of depth, physiological limit, and the simple fact that the openings observed in 1991 were too small for the equipment available at the time, and no subsequent dive has returned to probe them further. This is the contested territory in red snapper sink story, and the contention is not about the facts, but about how to categorize them. By some criteria, the sink has been opened. Divers physically descended into it, touched its floor, and made observations. That is more than has happened at most submarine karst features on the Atlantic shelf. But by the criteria that matter for understanding what the feature actually contains, the geometry of its deeper passages, the presence or absence of void space beyond the observed openings, the biological character of any water trapped in the lower chambers, the true depth of the karst development below the shaft, it has not been opened at all. The interior remains a hypothesis. The small caverns at the base exist in the record as visual observations, not as explored chambers with known dimensions and documented extent. What red snapper sink illustrates in this way is something important about how we should think about the Atlantic sealed submarine caves as a category. The line between explored and unexplored is rarely as clean as it sounds. A brief bottom contact dive is not exploration in the sense that cave scientists mean when they talk about mapping a system. Observation of an entrance is not the same as knowledge of what the entrance leads to. The 1991 work at Red Snapper Sink was technically demanding, genuinely significant as a geological investigation, and completely insufficient as a basis for claiming that the interior of the feature is understood. It placed divers at the threshold of something that remains, by every operational measure, unpenetrated and unknown. And Red Snapper Sink is not an isolated case on the Florida shelf. It is the best documented example of a class of features whose presence in the region is known but whose extent has not been systematically surveyed. The Florida platform is karst terrain, and the shelf that extends from it into the Atlantic is built on the same carbonate rock that produces springs, sinkholes, and cave systems across the Florida interior. Red Snapper Sink is where one of those systems breaks through into open water and becomes visible. The most dramatic surface expression of a geology that almost certainly continues to express itself, less visibly, across the rest of the shelf. Red Snapper Sink sits on a shelf built from carbonate rock that extends far beyond any single feature, and the broader question it raises is not really about one sinkhole off the Florida coast. It is about how much of the Atlantic continental shelf is underlain by karst that has never been mapped, never been entered, and in many cases never been specifically looked for. The honest answer, based on the available evidence, is that nobody knows, and the reason nobody knows is largely structural. Most of what has been found by accident. The pattern is consistent across the Atlantic margin. Fisheries surveys drag acoustic instruments across the seafloor and return data that was collected to count fish or assess bottom habitat. Geological cruises run seismic profiles to study sediment stratigraphy or fault geometry. Multi-beam sonar mapping campaigns produce high-resolution bathymetric charts as part of continental shelf delineation projects. In the course of all this work, anomalies appear. Circular depressions that break the otherwise flat gradient of the shelf. Acoustic shadows suggesting voids beneath the sediment surface. Abrupt depth changes that do not match the surrounding topography. These features get noted in field logs and occasionally described in footnotes. Sometimes they appear in supplementary materials in papers about something else entirely. What they rarely trigger is a dedicated cave investigation, because that is not what the surveys were designed to do. This is not a failure of scientific methodology, so much as a consequence of how ocean research is organized and funded. An expedition designed to characterize sediment thickness is not staffed or equipped to investigate potential karst voids. A fisheries trawl survey is not carrying the instrumentation needed to distinguish a genuine collapsed sinkhole from a pockmark left by escaping gas. The result is a literature full of incidental observations, brief references to unusual seafloor features that nobody followed up on, because the follow-up would require an entirely different kind of expedition. The catalogued sites, the ones with names and published descriptions, are almost certainly the visible edge of a much larger and mostly invisible population of features. The geological basis for expecting this larger population is well established. During the Pleistocene glaciations, sea level dropped repeatedly, in some phases by as much as 120 metres below its current position. The continental shelves were exposed. What is now seafloor was then dry land, subject to rainfall, groundwater infiltration, and the chemical dissolution of carbonate rock that creates karst terrain. Sinkholes formed, caves developed. Solution passages formed through limestone that today sits beneath tens or hundreds of meters of seawater. When sea levels rose again, as they did at the end of each glacial maximum, and most dramatically at the end of the last one, the karst landscape was drowned. The shelf became a seafloor, and the features it contained became submarine. The critical point is what happened next, or rather what did not happen. Karst preserved underwater in a low-energy sedimentary environment does not erode the way surface karst does. The voids are not flushed out or mechanically degraded by wave action or runoff. They fill slowly with sediment at their openings, which in some cases seals them rather than destroying them, protecting the void structure beneath the sediment cap. The ancient geometry of those features, carved when the rock was above sea level and subject to meteoric water dissolution, can persist largely intact for thousands of years on the drowned shelf. This is what researchers studying the Adriatic continental shelf found when multi-beam bathymetry revealed a series of circular depressions off Italy's Gargano promontory, features 70 to 160 metres deep, that have been interpreted as Pleistocene dolines, formed during low-stand exposure and preserved intact since the sea covered them. The Atlantic shelf's carbonate terrain has every reason to preserve the same kind of record. What makes the Atlantic case particularly compelling is the sheer extent of the shelf and the carbonate rock that underlies it, from the Florida platform northward, from the Bahamian bank system outward to the deep escarpment, from the karst terrain of Bermuda's platform down through the limestone sequences of the Bahamian archipelago. This is a geologically coherent zone of carbonate rock that has been exposed and redrowned repeatedly over the Pleistocene. The features that are known, the depressions on the Bahamian Escarpment, Red Snapper Sink, the mapped but mostly unentered caves around Bermuda, are separated by hundreds of kilometres of shelf that has received far less systematic scrutiny. The gaps between the known sites are not evidence of absence. They are evidence of incomplete survey. The sonar evidence that does exist supports this interpretation, but it requires careful handling. Multi-beam bathymetry and acoustic backscatter mapping can identify circular depressions, anomalous depth signatures, and features that are structurally consistent with collapsed sinkholes or karst voids. What they cannot do is confirm the presence of actual void space beneath the sediment surface, or distinguish between a true cave entrance and a pockmark left by fluid escape or gas seepage. The 29 abyssal depressions on the Bahamian Escarpment, ranging from 30 to 185 metres deep, with widths from 255 metres to nearly 2 kilometres, were identified from multi-beam and two-dimensional seismic data and interpreted as submarine karst features. That interpretation is the best available reading of the data. It is not the same as knowing what those features are from the inside, because no instrument has been inside them. The sonar-derived cave count may be an overestimate if some of the features are non-karst depressions. It may be an underestimate if there are additional voids whose surface expression is too subtle to register in the available datasets. The incidental nature of most discoveries matters for what this uncertainty means in practice. When a feature is found accidentally, during a survey designed for something else, the follow-up investigation almost never happens immediately, and frequently never happens at all. The feature gets catalogued. It appears in the literature. It sits there, described in terms of its surface geometry and acoustic signature, while the questions about its interior remain not just unanswered, but largely unasked. This is the condition of most Atlantic shelf karst that has been identified, known to exist in outline, unknown in detail, uninvestigated in any sense that would tell you whether the depression you can see on a sonar image connects to something larger and more complex beneath the seafloor. The cumulative picture is one of systematic underdocumentation. The features that have received names and dedicated investigations, Red Snapper Sink, the Bermuda cave systems, the Bahamian Escarpment depressions, are the ones that reached a threshold of attention that triggered targeted work. Below that threshold is a much larger population of anomalies, unnamed depressions in survey datasets, brief notations in cruise reports, references in geological papers to unusual bathymetric features that were not the focus of the study. Each of those represents a potential sealed karst feature that has not been opened, not been mapped from the interior, not been examined for the biological communities it might contain, and not been assessed for what it might reveal about the geological history of the shelf. The known sites are significant in themselves, but they are most significant as indicators, evidence that the process of karst formation and preservation on the Atlantic shelf operated widely, and that what has been found so far reflects the small fraction of the shelf that has been examined closely enough to reveal what the geology has been quietly preserving since the last time the sea pulled back and left the rock exposed to the dissolving power of rain. So we have this growing catalogue of sealed features, depressions, sinkholes, cave openings identified on sonar, systems that the geological record says should exist and in many cases clearly do. The reasonable question is why, given that we know where at least some of them are, nobody has simply gone in and looked. The answer is not a single obstacle. It is a compounding stack of them, and each layer of difficulty is more serious than it first appears. Start with depth, because depth is where most conversations about undersea cave exploration end before they begin. A significant portion of the Atlantic shelf cave systems that have been identified sit at depths beyond 300 meters. The 29 abyssal depressions on the Bahamian Escarpment range from roughly 30 meters at the shallow end to well over 100 meters deep into the escarpment wall, with the surrounding seafloor already at abyssal depths. Even the features that seem relatively accessible on paper are not accessible in practice. The current world record for a closed-circuit rebreather dive, the most advanced form of technical human diving available, stands at 316 meters. That is the absolute frontier of what the human body can withstand under pressure using the best available gas management technology, achieved under controlled conditions by an elite diver once. Most technical divers reach their physiological ceiling somewhere around 100 meters. Beyond that, nitrogen narcosis, oxygen toxicity, and the mechanical effects of pressure on the body become life-threatening rather than merely challenging. This is not a training problem or an equipment problem that better preparation can solve. It is a hard limit imposed by human physiology, and many of the sealed Atlantic features sit on the wrong side of that limit entirely. Red Snapper Sink offers a useful illustration of how depth alone can neutralize a determined attempt. When divers reached the site in 1991, the shaft measured somewhere between 460 and 495 feet deep, roughly 140 to 150 meters. That depth already pushed the technical diving equipment of the time to its limits, and the 1991 attempt only inspected the upper portion of the shaft. The lower chambers, where the shaft walls undercut into dolostone and the geometry of the system becomes genuinely unknown, were not reached. The depth that was accessible was already at the edge of what was safe. Everything below that edge remains unverified, not because nobody wanted to go there, but because the water column above those chambers extracts a physiological cost that current technology cannot fully offset. Depth alone would be enough to seal most of these systems against human entry. But depth is actually one of the more straightforward problems, because at least it is known and measurable. The structural conditions at cave entrances introduce a different category of difficulty. Many of the cave openings identified around Bermuda and elsewhere along the Atlantic margin are described in terms that make physical entry sound nearly impossible regardless of depth. Entrances are narrow, passages are constricted. Collapsed ceilings and debris fields have reduced what may once have been open mouths to tight throats, measured in meters or less. The research on Atlantic sea caves specifically notes that the walls are thick and the entrances are narrow, a description that sounds almost understated when you consider what it means in practice for any vehicle or diver attempting to move through them. A collapsed entrance is not just a tight squeeze, it is an unstable structure that can shift, a debris field that can rearrange itself, and a guarantee that anything entering will be doing so through a geometry that may not permit return. Then there is what waits inside. Deep karst water, particularly in ankyloline systems that have been sealed from surface circulation for extended periods, is frequently stratified in ways that are chemically hostile. Studies of Bermuda's submerged cave systems have documented depleted dissolved oxygen levels in the deeper reaches of known passages, with organic material accumulating in low-energy environments and progressively consuming available oxygen until the water becomes hypoxic or fully anoxic. Anoxic water does not just threaten biological life, it attacks equipment. Metal corrodes rapidly in oxygen, depleted chemically active water. Seals and gaskets respond unpredictably to environments they were not designed for. Sensors drift, cameras fog. The chemical stratification that makes these environments scientifically extraordinary, the sharp haloclines, the hydrogen sulfide layers, the microbial mats that form at chemically active boundaries, is also a systematic threat to any instrument package brought inside. This brings the discussion to ROVs, which are the obvious alternative to human divers and the technology that most people assume bridges the gap between what humans can reach and what needs to be explored. The reality of ROV performance inside cave systems is considerably more sobering than the technology's open water capabilities suggest. NOAA's own cave exploration work around Bermuda used small ROVs specifically because of the confined environment, but even purpose-selected small vehicles face constraints that the cave geometry does not forgive. A tethered ROV navigating inside a passage is trailing its umbilical through every turn it makes. In a tight, debris-strewn throat, that tether does not just create drag. It catches on edges, wraps around protrusions, and can trap the vehicle entirely. The thruster configuration that makes an ROV maneuverable in open water becomes a liability in a space where thrust in any direction risks pushing the vehicle into a wall or ceiling. The sediment problem compounds this significantly. Fine sediment accumulates on cave floors over thousands of years of isolation. It is extremely light, extremely fine, and responds to any water movement. An ROV's thrusters do not need to make contact with the floor to disturb it. The pressure wave from a thruster several meters away is enough to lift sediment into the water column and reduce visibility to effectively zero within seconds. Research on ROV operations in cave environments records exactly this. Vehicles stirring sediment and losing visual contact with their surroundings in what are called silt-outs. Inside a cave with no current to clear the water, that sediment stays suspended. Navigation becomes impossible. The vehicle is flying blind through a confined space with a tether dragging behind it and walls close enough to touch on all sides. This is not a failure of any particular ROV design. It is a consequence of the physics of enclosed water and fine particulate suspension that no current ROV configuration reliably solves. What this means in aggregate is that a cave can be known to exist, positively identified on sonar, described in published literature, assigned coordinates, referenced in expedition reports, and still remain effectively sealed to any meaningful investigation. Knowing a feature is not the same as being able to enter it, and the gap between those two conditions is not a small one. It is filled with depth limits, collapsed entrances, anoxic water, equipment failure modes, and the basic physics of trying to fly a tethered vehicle through a silt-floored passage without turning the interior into an opaque brown cloud. The Bermuda cave systems, the Bahamian Escarpment depressions, Red Snapper Sink, each of them is known. Each of them is in practical terms sealed. The catalogue of identified but unentered Atlantic cave features is not a list of problems waiting for someone with enough determination to solve them. It is a list of environments that are genuinely beyond the reach of what current technology can do safely or effectively. And what lives in those environments, what those chambers look like from the inside, remains as unknown as it was before the sonar ever swept across them. The inaccessibility of these systems is not only a technological frustration, it is a biological tragedy in slow motion, because the organisms that have adapted to live inside sealed cave environments are among the most scientifically extraordinary creatures on Earth, and the ones most likely to disappear before anyone documents them. To understand why, it helps to know what ankyline ecosystems actually are. The word ankyline comes from the Greek for near the sea, and it describes cave systems that have no direct surface opening to open water, but are connected to the marine environment through deep fissures in the rock. Water in these caves is not fully fresh and not fully marine. It is stratified, a lens of brackish or fresh water near the top, a sharp boundary called a halocline in the middle, and fully saline marine water below. That layering is stable over geological timescales precisely because nothing moves it. No tides stir the interior, no storms disturb the depths. The chemistry becomes its own closed world, and the organisms that colonize it have no reason to leave, and eventually no ability to survive if they did. Bermuda's submerged cave systems have been studied more thoroughly than almost any comparable environment in the Atlantic, and even that relatively thorough investigation reveals a picture that is startling. Biological surveys of the accessible Bermuda caves have documented approximately 75 species that are either restricted to cave environments or strongly dependent on them. 64 of those are crustaceans. Among them are lineages that were, until researchers pulled them out of these passages, completely unknown to science, including representatives of an entirely new order of crustaceans, Myctacea, whose existence was not suspected before cave biologists started working in Bermuda's submerged rock. The endemic isopod genus Atlanticellus was also described from these caves and found nowhere else on the planet. These are not slight variations on known animals. They are evolutionary departures significant enough to require new taxonomic categories. What makes this possible is isolation combined with time. When a cave system seals, whether through sea level rise flooding the entrance, collapse of the passage roof, or gradual sediment closure, the organisms inside begin adapting to their circumstances without any genetic input from the outside world. Over thousands of years, sometimes millions, that isolation drives divergence. Eyes become metabolically expensive in permanent darkness and are gradually lost. Pigmentation serves no survival function and disappears. The body reorganizes around different sensory priorities. Longer antennae for detecting chemical and pressure gradients, refined mechanoreception for navigating by disturbance in the water column. Metabolic rates drop to match the energy available in an environment where photosynthesis is impossible, and food arrives only as detritus sinking through fissures or as the products of chemosynthetic microbial communities operating at the system's chemical boundaries. That energy poverty is a defining constraint of cave life in darkness. Bermuda's ankyline caves are stratified not just in salinity but in chemistry, and the boundaries between layers are where microbial life concentrates, drawing energy from chemical gradients rather than sunlight. Hydrogen sulfide oxidation, methane cycling, and other chemosynthetic pathways support thin but real communities at these haloclines. The animals that graze on those microbial films have adapted to extract maximum return from minimum input. Low metabolic rates mean slow growth, slow reproduction, and long lifespans, a life history strategy that works well in a stable, sealed environment and fails catastrophically when that environment is disrupted. These organisms are exquisitely tuned to conditions that took geological time to establish, which is part of what makes them so fragile and so scientifically valuable simultaneously. The 2011 NOAA Deepwater Cave Expedition off Bermuda pushed to a maximum depth of around 448 feet, roughly 136 meters, and collected more than 50 specimens that researchers believe are likely new to science. That is a striking yield from a very limited penetration into a handful of cave entrances out of more than 150 mapped in the region. If even partial access to the periphery of these systems can produce 50 probable new species in a single expedition, what would full access to deeper, sealed passages reveal? That question cannot be answered with certainty, but the inference is not speculative in any irresponsible sense. It follows directly from what is already known about how cave isolation drives endemism, and from the observation that the Bermuda surveys have been confined almost entirely to accessible near-surface zones. The interior biology of the deeper passages, the sections beyond the collapsed throats and below the haloclines that current ROVs cannot reliably navigate, is genuinely unknown. Not theorized, not estimated, unknown in the strictest sense. The sealed systems of the Bahamian Escarpment and the deeper sections of Florida's karst shelf extend this uncertainty further. No biological surveys of any kind have been conducted inside the 29 abyssal depressions identified on the Bahamian Escarpment. There is no data because there has been no access. Whether those features host cave-adapted communities at all remains an open question. Some may be geologically young enough that colonization has not had time to produce the kind of deep endemism seen in Bermuda, and some may not be true voids at all, given the ongoing uncertainty about whether sonar-identified features represent genuine cave interiors or collapsed depressions. But the geological history of the region, the age of the karst formations involved, and the patterns established in every other isolated cave system studied globally, all point toward the same inference. If those voids are real and old, they are almost certainly inhabited by something that exists nowhere else. This is the biological case for exploration, and it deserves to be weighted alongside the geological one. Science's understanding of cave ecosystems has been built almost entirely from systems that humans could physically enter. Accessible inland caves, shallow coastal ankyline pools, cave systems reachable by technical divers within the limits of current physiology. Those environments have already demonstrated that cave isolation generates endemism at a rate that few other processes on Earth can match. Bermuda alone has contributed an entire new taxonomic order to the catalogue of life. The accessible portion of Bermuda alone. What the inaccessible portions hold is a question that current science cannot answer and current technology cannot resolve. The lineages that may have been evolving in complete darkness behind collapsed entrances and below navigable depths are not hypothetical in the way that speculative life on other planets is hypothetical. They are inferred from direct evidence of the same process operating in connected, partially explored systems. They are the most likely outcome of conditions that are known to produce them, in environments that are geologically old enough and sufficiently isolated to have done so. The organisms in Bermuda's surveyed caves are already telling a story about evolutionary divergence in sealed darkness. The 50-plus likely new species recovered from a single expedition's worth of limited penetration are telling that story loudly. What the deeper sealed passages of the Atlantic margin are holding, in the cold and the dark behind entrances that current technology cannot safely pass, is a continuation of that story, one that has been running for thousands or millions of years with no observer present, and that may have reached chapters science has never seen anywhere on the surface of this planet. Whether the sealed systems of the Bahamas and Florida's continental shelf represent similar biological repositories remains genuinely uncertain, but that uncertainty is precisely the reason the biological argument for finally breaching these seals is not secondary to the geological one. It is at least equal to it, and by some measures considerably more urgent. The biological urgency just described runs directly into a legal and administrative structure that sounds, on its face, like exactly the right response to that urgency. These habitats are protected. The law says so. And that is where the real problem begins, because legal recognition and genuine management are two very different things, and in the case of sealed underwater caves along the Atlantic margin, they have almost nothing to do with each other. In Europe, the framework is explicit and substantial. The EU Habitats Directive designates submerged and partially submerged sea caves as a priority habitat type under Annex 1, catalogued as Habitat Type 8330. That designation has produced 434 Natura, 2,000 sites specifically identified for the protection of underwater cave habitats, 434 designated areas. That is not a minor or obscure classification. It represents a formal commitment by European member states to protect these environments from degradation. Across the Atlantic, the United States has its own version of this framework. State-level marine protected areas include cave habitats within their protected zones. California's Blue Cavern State Marine Conservation Area, to take one example, lists underwater caves explicitly among the features it protects and prohibits any injury, taking, or disturbance of geological resources within its boundaries. These are real legal instruments, and they carry real prohibitions. They're not merely aspirational, but there is a foundational assumption embedded in how that protection actually works, and that assumption, when applied to sealed or unmapped cave systems, creates a kind of administrative fiction, a gap between what the paperwork says and what the protection actually accomplishes. The assumption is this, that the rock surrounding a sea cave naturally insulates whatever lives inside. European designations, as researchers reviewing the Atlantic cave literature have noted, tend to treat protection as something that flows automatically from the cave's physical structure. The walls shield the interior, the sealed entrance prevents disturbance, and therefore the contents are protected by default. What is visible from the entrance, or inferable from the entrance geometry, becomes the basis for the designation. What lies beyond the entrance, in the deeper passages, in the sealed chambers, in the sections no diver or instrument has ever reached, that is treated, implicitly, as falling under the same umbrella. This logic is not unreasonable for caves whose geometry is well understood. If you know the cave's extent, know what lives inside it, and know the pathways by which external stresses could reach the interior, you can design management measures around that knowledge. But for sealed caves, for the more than 150 mapped but unopened systems around Bermuda, for the 29 abyssal depressions on the Bahamian Escarpment, for the deeper chambers of Florida's Red Snapper Sink that the 1991 exploration only partially reached, there is no such knowledge. The geometry is unknown. The resident communities, if they exist at all in the deeper sections, are unknown. The connectivity between the cave's water column and potential contamination pathways is unknown. You cannot manage what you cannot measure, and you cannot measure what you cannot access. The result is not malicious neglect, it is structural blindness. These habitats are protected on paper, and in a narrow technical sense that protection may be real. Activities directly targeting the cave entrance may be prohibited, and outright destruction of the surface feature may be restricted. But the protections are built around the visible and the accessible, and they leave the invisible interior in a kind of administrative shadow. That shadow has a texture, and it is not merely theoretical. NNOAA's cave biology documentation from the Bermuda expeditions enumerates the threats facing Ankylan cave systems with uncomfortable specificity. Sewage discharge and waste dumping introduce nitrates and phosphates into groundwater systems that are hydrologically connected to submerged cave water columns, even where the surface connection appears sealed. Deep well injection, a common waste disposal method in carbonate island settings, can push toxic metals, pharmaceuticals and organic contaminants directly into the groundwater at depth. Limestone quarrying and construction on the surface fractures rock and disrupts the hydrological boundaries that maintain the chemical stratification inside Ankylan systems. The organisms that evolved in these systems over millions of years, the remipedes and thermospanations and crustaceans with no eyes and no means of leaving, cannot relocate when the chemistry of their water changes. They are fixed in place, exquisitely adapted to conditions that are being altered from the surface with no monitoring, no baseline, and no possibility of detecting the change until it is already irreversible. On the continental shelf, the threat profile shifts but does not diminish. Offshore drilling and the sediment disturbance associated with seabed infrastructure are not abstract risks in the Atlantic. Research into deep marine carbonate formations has shown that drilling-related compaction and shear stresses are among the primary mechanisms that trigger collapse in submarine karst systems. A sealed cave whose roof was stable for millions of years can be destabilized by pressure changes introduced by nearby drilling operations. The problem is not just that the cave might be destroyed. The problem is that no one would know the cave existed in the first place, which means no one would have flagged it for protection, which means the activity that destroyed it would have proceeded with full legal authorization. A sonar signature that might represent a sealed void, or might represent a collapsed depression, or might represent a true cave-hosting endemic fauna, is not a sufficient basis for drilling exclusion zones under any current regulatory framework, particularly when the uncertainty itself, the fact that the feature is unconfirmed, becomes a reason to defer rather than investigate. Climate change adds another layer that management frameworks are entirely unequipped to address. Ocean warming, acidification, and changes in deep water oxygen content are already measurable across the Atlantic margin. Anchialine systems are sensitive to temperature and chemistry gradients that have been stable for geological periods. As those gradients shift, as warming surface waters change the thermal profiles that propagate downward through fractured limestone, as acidification alters the carbonate chemistry of the rock itself, the conditions inside sealed caves will change in ways that no one can currently detect, because no sensors are inside those caves and no baseline measurement has ever been taken. The organisms inside have no evolutionary preparation for these changes. They have never needed it. This is the conservation blind spot in its fullest form. It is not that these habitats are unprotected. It is that protection, as currently structured, operates entirely at the boundary between the known and the unknown and stops there. The legal designation covers what has been observed and catalogued. The assumption of natural insulation fills in the gap between the entrance and the interior. But that assumption is doing enormous work, and it is doing it without any factual support, because the interior of most of the systems has never been observed, catalogued, or measured by anyone. Genuine management would require at minimum knowing what is inside. It would require understanding the hydrological pathways that connect the cave water column to surface inputs. It would require baseline chemistry and temperature profiles that could be used to detect change. It would require some knowledge of whether the resident community, if there is one, overlaps with the stygobiont fauna documented in Bermuda's accessible sections, or represents something entirely different. None of that information exists for the sealed systems, and so the protection that exists is in practice the protection of an outline, a boundary drawn around something whose contents remain in the strictest sense unknown. The name on the map is not the same as knowledge of what the map contains, and for these sealed caves, across Bermuda, across the Bahamian shelf, along Florida's karst margin, the map is still almost entirely blank. That blank map is not a permanent condition. The tools to begin filling it in exist, or are being developed, and understanding what they can and cannot do is essential to any honest discussion of whether these sealed systems will ever be opened, and what opening them would actually require. Start with the technology that is furthest along. Mixed gas closed-circuit rebreathers. Modern CCR systems recycle exhaled gas, scrub out carbon dioxide, and precisely manage the oxygen fraction in ways that dramatically extend both depth range and bottom time compared to conventional open-circuit scuba. Experienced cave divers using these systems have pushed well beyond 300 meters in open water, and their use in cave environments has steadily extended the frontier of what is physically reachable. For shallow sealed shafts along the Atlantic margin, features whose entrances sit in the 20 to 80 metre range, next-generation CCR equipment genuinely changes the calculus. A diver team equipped with mixed gas rebreathers, the right bailout configuration, and adequate surface support could potentially make a first penetration of an entrance that was simply unreachable with previous technology. But reachable and fully explorable are different things. The Red Snapper sink descends past 400 feet before its lower chambers were even partially assessed in 1991, and what the 1991 team found was not a shallow system with a simple geometry. It was the beginning of something larger, deeper, and more complex than the available tools could follow. Modern CCR systems would extend that reach, but the decompression obligations at those depths accumulate quickly. The time available at maximum depth shrinks even with the best gas management, and the logistical requirements, boat support, gas supply, safety divers, the sheer weight of equipment, scale with the depth in ways that are not easily solved by equipment improvements alone. Rebreather technology is a meaningful advance. It is not a solution to the access problem for the deepest sealed systems. That is where remotely operated and autonomous vehicles enter the picture, and where the expectations have to be calibrated carefully. Small work-class ROVs with depth ratings down to 3,000 meters already exist and are operational. Vehicles like the FCV-2000D can carry multi-beam sonar, high-definition cameras, and sampling instruments to depth that no human diver will ever reach. The problem is not depth capacity, the problem is geometry. Most of these vehicles are roughly 3 meters in length. They're designed for open water and seafloor inspection, not for threading through the kind of narrow, irregular passages that define the interior of a karst cave system. An ROV that can descend to the Bahamian Escarpment and hover above one of those 29 giant depressions is not the same tool that can navigate the passage behind the entrance. If the opening is wide enough, a work-class ROV can look inside. Whether the interior network is accessible to it depends entirely on how the cave's geometry evolves past the threshold. Purpose-built cave-capable autonomous underwater vehicles are a more promising avenue, and development is underway. Systems like Cave PI are being engineered specifically for tight space navigation, using semantic guidance algorithms and onboard perception to interpret complex void geometries in real time, without relying on a tether connection that would snag on rock. The concept is genuinely suited to the problem. A vehicle small enough to fit through cave passages, smart enough to navigate them without human intervention at the surface, and equipped to map and sample what it encounters. The caveat is that these systems are still in development, and the gap between a research prototype tested in known training environments and a deployable instrument ready for the first penetration of a sealed abyssal karst feature is not a small gap. The engineering challenges, power management, acoustic communication through complex rock geometries, recovery if the vehicle becomes lodged, are real and not yet fully solved. A third approach is more unconventional, but has already been demonstrated in practice. Researchers studying the Sancha Yongle Blue Hole in the South China Sea mounted a miniature drilling rig directly onto an ROV and successfully retrieved 5-centimeter diameter sediment cores from the interior walls at depths of 116 meters. The technique worked. It produced geochemical data that could not have been obtained any other way. For the sealed offshore systems along the Atlantic margin, the Bahamian depressions, the unmapped chambers beneath the Bermuda carbonate platform, a scaled version of this approach could in principle provide interior access without requiring a vehicle to navigate through the cave itself. You drill through the cap, you sample what is below. The access point is not the entrance, it is a purpose-drilled borehole from above. the practical scaling problems are significant. The Sancha Yongle demonstration involved a relatively shallow system with stable wall geometry. The Bahamian abyssal pockmarks sit at much greater depth under different pressure regimes, and their structural integrity, whether the walls and ceiling of whatever void may lie beneath the surface, depression are stable enough to withstand drilling-related vibration and pressure change, is not known. Larger rigs, more precise positioning, detailed stability analysis of the specific target site. These are prerequisites that take years to develop, not obstacles that can be overcome by wanting to try. And then there is the question that the technology discussion cannot sidestep, whether breaching a sealed environment by any means is something that should happen before the environment is understood. The anoxic water columns inside some of these systems, conditions that have likely been stable for thousands or millions of years, are not passive voids. They host microbial communities and carbonate formations that have never encountered external disturbance. Introducing an ROV, drilling through a cap layer, even sending a diver team through a newly accessible entrance, carries the risk of introducing contaminants, altering the chemical stratification that defines the habitat, and collapsing walls that have been under equilibrium load for geological time. Existing marine protected area regulations would apply to many of these sites, and activities that constitute disturbance of geological or biological resources may be prohibited under frameworks that were written precisely because these environments are presumed to be fragile. The answer to this tension is not to do nothing. It is to recognize that genuine exploration of sealed Atlantic cave systems is not a single-step problem. A realistic pathway begins with the tools that create the least disturbance, high-resolution multi-beam and side-scan surveys to locate viable entrances and distinguish true cave voids from collapsed depressions, building on the work that NOAA's Bermuda expeditions began and that the Bahamian Escarpment sonar surveys continued. That survey phase informs which sites are candidates for any physical access attempt. For shallow systems where entrance geometry permits, mixed gas CCR teams provide the first look, with sampling and documentation protocols designed to minimize impact. For deeper branch penetration where human divers cannot follow, mini ROVs or cave PI-type autonomous vehicles take the survey further, and where physical entry remains impossible, targeted ROV-mounted borehole sampling offers a geochemical window into the interior without requiring navigation of the passage network at all. Each of those steps feeds the next, and each carries its own set of prerequisites: geological modelling, vehicle testing, regulatory review, conservation risk assessment. None of them are imminent. The technology is advancing, but the specific combination of capability, access logistics, legal clearance, and ecological understanding that would allow a first confirmed penetration of the most sealed systems along the Atlantic margin does not exist today. What exists is the beginning of a framework for thinking about how it might be assembled. The blank map will not fill itself in, but the tools that could begin to fill it are, for the first time, at least imaginable in concrete form. So the tools are imaginable. The pathways are beginning to take shape. But before any expedition reaches a sealed entrance, before any autonomous vehicle threads its first passage, it is worth sitting with a harder question. What would it actually mean to get inside? Not in the abstract sense of scientific progress, but in the specific concrete sense of what changes for geology, for biology, for conservation law, for our understanding of the Atlantic seafloor itself, the moment confirmed first entry is achieved. The geological implications alone would be substantial. The Atlantic margin karst record is understood almost entirely through exposed systems and partially accessible caves like those in Bermuda's Walsingham network. But the sealed chambers beneath the carbonate platform, the unmapped passages that NOAA's 2009 and 2011 expeditions identified and could not enter, the 29 abyssal depressions along the Bahamian Escarpment that sonar has outlined but no instrument has penetrated. These systems sit outside the current model almost by definition. What we know about Atlantic karst landscapes has been constructed from what we've been able to reach. The sealed portions represent a gap in that model, not an extension of it. Entering one of those systems would not simply add a data point. It would test whether the model itself has been built on a representative sample, or whether the accessible caves are outliers, and the real structure of Atlantic karst lies in the portions that have never been touched. The climate archive question is even more pointed. Bermuda's accessible caves have already demonstrated their value as paleoclimate records. Benthic foraminiferal assemblages recovered from Green Bay Cave trace the Holocene transgression through distinct faunal zones, and sediment evidence from the Walsingham system has yielded data pointing to a sea level approximately 21 meters higher than present during marine isotope stage 11, a finding with direct implications for long-term ice sheet dynamics. If the accessible caves have already produced this level of resolution, sealed systems, where the sediment column and the speleothem record have never been disturbed by any external intrusion, could preserve a climate archive of extraordinary fidelity. Foraminiferal tests and speleothem isotopes locked inside a closed geochemical environment offer high-resolution proxies of historic ocean chemistry, temperature, and nutrient flux in a form that open water sampling simply cannot replicate. A sealed Atlantic cave system with an intact sediment record is not just an interesting geological feature, it is potentially a continuous geochemical bridge between marine and terrestrial climate archives, filling intervals and filling gaps that no other source material can address. And then there is the biological question, which may carry the most immediate stakes. Bermuda's known submerged cave network already hosts 78 stygobionts species, organisms adapted to live permanently in cave waters with no capacity to survive or reproduce in open marine environments. 65 of those species are endemic to Bermuda. 25 are listed as critically endangered on the IUCN Red List. These are not marginal populations clinging to a degraded habitat. They are highly specialized fauna that evolved in the specific chemical and physical conditions of ankyloid cave systems over enormous spans of time, and they exist nowhere else on Earth. If the accessible portions of Bermuda's cave network support communities of that richness and that degree of endemism, the sealed deeper systems, where conditions are likely more extreme, the isolation more complete, and the evolutionary trajectories longer, almost certainly host fauna that nobody has ever catalogued. Not variants of known stygobionts, potentially entirely new lineages representing evolutionary histories that have played out in absolute isolation from the surface world. First entry into a sealed system carrying those kinds of organisms would not be the discovery of a new species. It could be the discovery of an entire ecological structure that has no analogue in the documented record. That prospect changes what discovery would mean in another, more complicated direction. A first entry that confirmed unique biodiversity, intact climate records, and an undisturbed geochemical environment would not just generate scientific papers, it would generate a regulatory problem. Many Atlantic submarine cave features are already covered by legal frameworks, US Marine Protected Area designations, the EU Habitats Directive, that nominally extend protection to sea caves as a habitat class. The problem, as has been documented, is that the interiors are unseen. Protection without knowledge of what is being protected is not active management. It is a placeholder. The moment confirmed evidence of extraordinary endemic fauna or irreplaceable sediment archives surfaces from a first entry expedition, the regulatory pressure to formalize and actively enforce that protection would increase sharply. Stricter access restrictions, mandatory review processes for any future penetration attempt, potential redesignation of specific sites as no-entry reserves, These are not hypothetical outcomes. They are the predictable institutional response to documented, irreplaceable value. Discovery could close doors as decisively as it opens them. There is also a more subtle distinction that the drama of first entry tends to obscure. Finding a spectacular void, documenting a chamber, photographing fauna, recovering a sediment core, is not the same as understanding a network. The sealed systems along the Atlantic coast are not isolated pockets. They are to the extent that the geological modelling allows any inference, components of interconnected karst systems whose full geometry extends beyond any single entry point. The Bahamian abyssal depressions are grouped in a cluster pattern that suggests shared formation processes and potentially shared subsurface connectivity. Bermuda's unmapped deep passages almost certainly link to the known cave network in ways that partial surface surveys cannot resolve. Entering one chamber answers the question of what is immediately accessible. It does not answer the question of how far the network extends, how the hydrology connects across the carbonate platform, or whether the organisms living in the first chamber accessed represent a population or a fragment of a much larger hidden community. The scientific value of first entry is real, but it is the beginning of understanding, not the completion of it, all of which means that the stakes of breaching any of these sealed systems are genuinely layered. Geologically, the potential is to rewrite the current model of Atlantic karst, to discover that the landscape we thought we understood was built on an incomplete sample, and that the sealed portions contain structural and stratigraphic evidence that changes the map fundamentally. Biologically, the potential is to encounter fauna representing evolutionary trajectories that have never been exposed to the surface world, endemic species whose existence changes IUCN assessments and conservation priorities across the region. Climatically, the potential is to recover archived material that fills specific gaps in the Atlantic paleoclimate record with a resolution and continuity that no other source can provide. And ethically, the stakes are this: whatever enters first, and however it enters, will alter conditions that have been stable for timescales that dwarf the history of human exploration, the anoxic water columns, the chemical stratification, the undisturbed sediment surfaces. These are not passive voids waiting for a visitor. They are functioning systems shaped over deep time, whose fragility is proportional to exactly the isolation that makes them scientifically extraordinary. The question is not only what we would find, it is whether we can enter without destroying what makes the finding meaningful. That is not a reason to stay away indefinitely. It is the most important design constraint for any expedition that eventually goes in. Here is what we can actually say with confidence, and here is where the honest account of this subject has to stop and hold its ground. NOAA's 2009 and 2011 expeditions around Bermuda identified more than 150 limestone caves, mapped 161 specific points of interest that could represent deep water entrances, and then, after deploying ROVs and conducting the most systematic survey of the island's submerged cave systems ever attempted, confirmed only 7 candidate sites worth pursuing further. Most of those turned out to be tunnels less than a metre wide. One system, Green Bay Cave, has been surveyed through more than 2 kilometres of passage and stands as the only fully entered deep water cave Bermuda has produced. The rest remain sealed. Not theoretically sealed, not sealed pending a permit review, but physically inaccessible to any instrument or diver currently operating in that environment. That is the strongest documented evidence for the existence of real, unopened subterranean systems on the Atlantic coast, and it rests on the work of one of the most rigorously documented oceanographic programs in the region's history. Off the Bahamas, the picture is compelling but less certain. Seismic and bathymetric surveys of the Black Bahamian Escarpment have identified 29 abyssal depressions, some reaching 185 meters deep and nearly 2 kilometers wide, clustered along a carbonate margin at depths between 4,584 and 4,967 meters. The researchers who analysed those surveys interpreted the formations as collapse-generated voids with structural characteristics consistent with sealed submarine caves. No ROV has reached any of them. No instrument has confirmed what lies inside, or whether there is a continuous interior void at all. The sonar signature is real. The interpretation of that signature as a sealed cave-like system is the researchers' best inference from the available data, and it may be correct, but it is an inference. Sonar does not distinguish cleanly between a true enclosed void and a collapsed depression that only resembles one from above. The Bahamian features are the most dramatic candidates on the Atlantic margin. They are not yet confirmed caves in the full sense of that word. Florida's red snapper sink sits somewhere between those two cases. Technical divers reached the bottom of that karst shaft in 1991, documented a sand-covered floor at around 460 feet, and observed small caverns at the base. That is confirmed access to the upper portion of the system, but the shaft is estimated to continue far deeper into older rocks, and that deeper interior has never been penetrated. Whether the lower system connects to larger chambers or represents a simpler vertical structure that pinches out at depth, nobody knows. The 1991 dive answered the question of whether the shaft was accessible at all. It didn't answer the question of what the shaft contains. So the honest classification is partial access, known upper section, unknown interior, which is a fundamentally different status from either Green Bay Cave or the Bahamian abyssal features, and that distinction matters more than it tends to get acknowledged in broad claims about unexplored underwater caves. The uncertainties that sit underneath all three of these cases are not peripheral details. They are load-bearing parts of the story. The exact number of sealed caves along the Atlantic margin could be over or underestimated depending on how sonar signatures are interpreted and how strictly the category of sealed cave is defined. Some sites labelled as never opened have had brief instrumental contact, an ROV camera glimpsing a tunnel entrance, a diver touching a shaft floor without penetrating. And the line between first access and genuine first entry is less clear in practice than it sounds in description. The biological surveys that document extraordinary stegobiont diversity in Bermuda's accessible caves provide strong circumstantial evidence that sealed deeper systems host undiscovered fauna, but they are still circumstantial. The organisms in the sealed chambers have not been collected. Their existence is the most reasonable scientific inference available, not a confirmed observation. What does survive all of that qualification is something worth saying plainly. Modern oceanography has mapped the Atlantic seafloor at resolutions that would have seemed impossible 50 years ago. Multibeam sonar, sub-bottom profiling, and satellite-derived bathymetry have together reduced the number of places on Earth that are simply unknown in any sense. And yet the Atlantic coast, one of the most studied ocean margins on the planet, still contains cave systems and karst features whose interiors have never been reached. Not because nobody noticed them, but because the tools required to enter them do not yet exist in deployable form, or exist in prototype form that has not been adapted for this specific application, or exist in theory but not in the engineering reality of sustained deep-water cave penetration. The frontier here is not geographic, it is technical and it is real. What makes these systems compelling, and this is the thought worth sitting with at the end, is not the scale of what might be hidden inside them, though that scale is genuinely large. It is that they are only partly legible. We know where several of them are. We have their rough dimensions in some cases, their surface morphology, their regional context. We have biological evidence from adjacent accessible systems suggesting what kinds of life they might harbour. We have a geological framework that explains how they formed and why they have stayed closed, and we know almost nothing about what the sealed portions actually contain, because no instrument capable of crossing that threshold has crossed it. That is where the investigation stands. More than 150 caves mapped around Bermuda, the majority never entered. 29 abyssal features in the Bahamas that may be the largest sealed submarine cave systems ever identified, none of them accessed. A Florida karst shaft whose upper section was reached in 1991, and whose lower interior remains entirely unknown. These seals are real. The question of what lies behind them is open, and the expedition that finally answers it has not yet been planned.